So what I've shown you so far is how to convert between the Cartesian and the polar coordinate system. And well, you already knew how to integrate in the Cartesian coordinate system, but I also showed you now how to integrate in the polar coordinate system. So, you can actually now, in principle, take a function that is defined in Cartesian coordinates in terms of x and y. You can convert that into a function of polar coordinates r and phi, and then integrate using polar coordinates. But what if you don't have an integral, but we actually have something with derivatives? And in fact, in physics, what we have very often is equations with derivatives. So for example, what I show here, that is not just a part of an equation, but one where I have dx squared plus dy squared of a function f that depends on both x and y. That is, for example, you have the Poisson equation, or also the Schrödinger equation in quantum mechanics. That is an important part of the equation. So that is, typically when you see this definition, you see it in Cartesian coordinate system. But how would that equation actually look in another coordinate system? And what we need to do for that is that we need to convert now the derivatives from the Cartesian coordinate system into the polar coordinate system. And well, there are different ways of doing that. What I want to only show you here is basically the most direct method, and that is a direct calculation. So what we want to do is we want to, so we're not going to do the full equation that I show here, but I'm just going to show you how to do parts of it, and then actually to do the actual calculation that's part of the homework exercises or the exercise that you can do in the exercise class. But what we actually want to calculate is we want to know what actually happens when I apply derivative in Cartesian coordinates such as d dx to a function in polar coordinates. Because that's then what you can do is you can basically substitute here this function in Cartesian coordinates by this other function with polar coordinates. But then how should we actually do that? Because, now you have d dx, but here you have r and phi. So how should we actually do this differentiation? So it's actually not clear. It's not clear at all if you look at this form, how to calculate the derivative. And, for it to become clear, what we need to do is we need to write things out a bit more clear, because what we actually, when we write something like that here, we're actually being sloppy. And it's actually good to be sloppy for convenience, but sometimes it's good to be actually very precise, because then we see more clearly what we need to do. So, and for that, what we actually need to see is what is the relationship between f of x, y and f of r phi. Because although I actually write f of x and y and f of r phi with the same symbol, simply f, these are actually two different functions. Well, you can actually easily imagine, let's say you have a function which is f of x, y equals to x squared plus y squared. Well, if I convert that to polar coordinates, I simply get f of r and phi equals to r squared. And you see that, of course, here already the function itself looks very different. So the function f of r and phi is actually not the same in terms of, just algebraic terms as the original function. So what is actually the exact relation between those two? So the exact relation between those two is that I have a function f that is defined in Cartesian coordinates, and I'm explicitly taking this into account in my notation, and I call this now f Cartesian of x and y. And I want to have a f in polar coordinates, so this is now again in a different function f polar, such that when I go to the point r phi, which corresponds to the point described by xy, I get the same function value. And for that, it is very it's important to also now remember that r can be expressed as a function of x and y, and so does phi. This is the relationships that I gave above. So the r equals square root x squared plus y squared, and phi equals to the arctangent of y divided by x. So that if you now write this down very explicitly, we see that now we have a function of x and y on the left side, and we have a function of x and y on the right side. And now we can actually more clearly see how this equation looks like. So as I said, in physics, we're usually sloppy. And we simply write f of x, y equals f of r and phi. But what we actually mean by writing that is we mean this. But knowing that, we can actually now calculate this derivative here explicitly, because now we actually have an expression here which is defined in terms of x and y again, and then we can apply the derivative to that. So for that, what we now do is we take dx f of r and phi, and now we simply what we do is we write things more explicitly, and we write this as dx f of r of x, y, and phi of x, y. And now we want to take this derivative here, ddx. Now, in order to take this derivative, we need to go back and just remember how to take a derivative of a function which depends on more than one variable. So in school, we already learned how to take derivatives of function with one variable. Now, if you have a function that maybe depend on several variables, well, what do you have to do then? Well, in the end, it's actually quite simple. And I give the generic formula here at the bottom. So what we actually have here is not just, we have a function that takes as an argument another function. So we actually have the chain rule, but basically the chain rule for a function with several coordinates. And so I give the generic function down, the description of taking this chain rule for a multivariable function down here. But in the end, what you need to do is you need to take the derivative with respect to every of these variables and multiply with the derivative of the inner function that you have here. So first, what we see is we have here f of r of x and y. So what we need to do first is we take the derivative of f with respect to r. And then we have to take the derivative of the inner function, which in this case is dr of x and y dx. And then we need to do the same for phi, and then we get df d phi times d phi of x, y dx. And now to simplify this expression further, what we now need to do is we need to go back to the definition of, what was r in terms of x and y, and what is phi in terms of x and y. So that we can just quickly go back in our lecture notes. And we see that, well, this was these expressions here. So you need to take the derivative with respect to square root and x squared plus y squared. So that is relatively simple. And you also need to do this for the arctangent. So there you might actually want to look up maybe what is actually the derivative of the arctangent, but then it's also a simple calculation. And then you can easily calculate this expression here. And once you did that, what you can do is you get some expression here in terms of x and y, and here something in terms of x and y. You can now actually use the inverse relations again, x in terms of x and y in terms of the polar coordinates, to reduce this whole expression here to only have polar coordinates anymore. And then you see that we basically went from Cartesian coordinates. So here we started off with the ddx. Here we only have a dr and a dd phi anymore together with, you know, some expressions which depend on r and phi. And in that way, you can systematically convert the derivative for from these Cartesian coordinates to the polar coordinates. Now, to do the full Laplacian that I showed here, that's a little bit tedious because you just have lots of terms. I mean, as you see already, when you do that for just a single derivative, you get 2 terms. If you do, you know, ddx squared, you get 4 terms, and then you have to plus dy squared. You get quite a few terms, but in the end, to do this exercise, it's actually 2 of the exercise problems that we pose you deal with exactly that problem here. When you do this problem, you'll actually see that in the end, it simplifies to something which is very compact. So although the calculation is a little bit tedious, I highly recommend doing that exercise because, you know, only by, you know, Xing it out in detail once you can really learn how to do these conversions.